Hello, as you can see in my title, today I will talk about what is derivative, why we should care about them, and how we can calculate them. So I will start this presentation from the first question I impose in my title, what is derivative about? So derivative is about how fast something is moving. To measure or you to calculate how things move around us, we use this concept of derivative. So derivative is in almost every field, but it has different names, in other field. For example, you might have seen with the derivative this name instantaneously rate of change in some fields. In some field, its name is a velocity. In some field, it is known as the slope of tangent line, and sometimes we call it as the rate of interest. For example, in business, and sometime in other field, for example, in economics, the derivative is known as marginal cost. So derivative is in almost every field, but it has a different name in different field. Okay, next let me introduce you this notion of derivative, or that is this concept of derivative. As I said in my first slide, derivative is about how fast things change. And when we say this word, how fast things change, we also sometimes call or name them the rate of change. You know, what is the rate of change? Something what is moving or something is changing. So, in order to understand the derivative, we need to first understand this concept, the rate of change. So, rate of change, uh, when change happen, it always happen in comparison to something else. So, for example, if you're traveling in a car with your friend, your position is not changing in comparison to your friend, but your position is changing in comparison to something else on the road. So change always happen, and it has happened always in comparison to something else. So for our convenience, what we do, these changes, we define a relationship, and that relationship is what we call rate of change. So rate of change give us a relation between two things, and it tell us how one thing change in comparison to another. For example, if I establish a relationship between distance and time, and I will define it as the change in distance divided by change in time. So this relations will tell me that in comparison with time, how fast and the slow distance will change. So this is a very useful relation for us. Like for a 2 minute, if I ask you to forget that concept of speed, and then I ask you the question, if you have to travel from a city 1 to the city 2, and tell me how much time it will take you from traveling from the city 1 to city 2. And you will be surprised. This is not an easy question to answer without the concept of speed. So this concept of speed is a help us. It is a relation which is a help us to solve many problem in our real world. And this rate of change has two flavor. So one is the average rate of change, and the second one is the instantaneously rate of change. So this instantaneously rate of change is which we gonna call later derivative. But in order to understand this instantaneously rate of change, first we need to understand what is the average rate of change, and also we need to understand why we need actually the instantaneously rate of change. you know so for average rate of change, now let's assume you are traveling from the city A to the city B, and the distance between the city A and B is 120 miles, and if you cover this distance in 2 hours, and if I ask you to find the speed, so you will say the speed will be the change in distance, because that is the relationship of the speed we define. How much distance is change from the position A to the position B, and the change in time from the position A to position B. And if we use this formula, we will get our speed 16 mile per hour. I want you to notice in this formula, there are two main things to notice in this formula. The first one is, in order to compute the speed or the rate of change, you need 2 points. You need a point A and the point B. So the rate of change is not a single entity, it is two entities. For example, the distance is a single entity, so you can measure the distance independently. Time is a single entity, you can measure the time independently. But the rate of change is, you need 2 points. It's not a single entity. So you need a point A and you need a point B. So you need change here and something is happening change there in order to use this formula. And the second thing you should notice in this formula is, this formula give us the average rate of change. And for example, in case of speed, this is 60 mile per hour. This is your average speed. So what is average speed? On an average, you are traveling 60 mile per hour. Or in other words, in 1 hour, you are traveling 60 miles. So you may be going slow and fast between the position A and position B, but on an average, your speed is 60 mile per hour. And in many situations, this is enough information, or this is the sufficient information for us to solve our real world problem. For example, the question I impose in the beginning, that if you have to calculate how much time it will take you for grow from one city to another city, if you have an average speed, you can answer that question. So now assume another situation. There was an individual, he or she was traveling from position A to B, but that individual got into an accident at some time, let's suppose t is equal to 60 minutes. And now if I ask you, can you tell me by using the average speed of the person, how much damage happened? Or how much damage happened to these two individuals who were involved in that accident? Or in other words, like, do you think the average speed is enough to make that conclusion, or you make at least a rough estimate how much damage has happened? Do you need the average speed or you need some else speed? And that bring to the main question of this calculus and this concept of derivative. No, you need the speed at that moment. You need the instant speed, instant rate of change. That's what we need in order to know what was happening or how much damage was happening at that point. So this is the main and this is the central question of the calculus or the concept of this derivative. Now you may be thinking that what is the big thing about this and why we cannot calculate it. So now I want you to think that if you really try to calculate, you will find it hard. What is the distance change in that moment? Is zero, because you have only 1 point at that moment. There is no change in the distance. And what is the change in time at that moment? That is also zero. So if you try to use this formula and calculate it, your instantaneously rate of change will be 0 over 0, which is a meaningless. So that was the main question came out. How to calculate that instantaneously rate of change? It took many centuries to our forefathers to come up with an idea how to calculate it. It was not an easy question. It took many years, many centuries actually, to find, actually finally to how to find the instantaneously rate of change. And first time formally, the idea which came to us, like how to calculate this instantaneously rate of change, this idea was formally was written by these two scientists, the Newtons and the Leibniz. There are some controversy between who wrote that idea first, but we're not going to talk about this controversy today. But these were the two our forefather who basically formally wrote this idea. So next we're going to talk about this idea. What was this idea? The main idea. which give us the concept of derivative. So talking about this idea has a three step or three rule. So our forefather said if you use these three rule um, without asking too many questions, you will be able to find that instantaneously rate of change which we are looking for. So nothing too serious happen in between two step or the two rule, but there is something is a magic happens at the third step. You know, the third step is the main step in this sort of a whole big idea, which is behind the concept of derivative. So before I give you this idea, I want you to go into a state of imaginations. So if you think a bit more rigorously or more like logical, this is you may miss the whole idea. But what I want you to do is I want you to sort of imagine, go into a state where you can imagine things, things like a poet. So what is this idea is about? So so as we see that when we were calculating the average rate of change, we need 2 point. We need, the change happens, something is changing here and something is changing there. So you need 2 point in order to use that formula, and we have only 1 point if we want to compute the instantaneously rate of change. So what they suggest us assume there is a second point which is extremely close to the first point where you want to compute your instantaneously rate of change. You close which is so close but still there is a non-zero distance between them. So that is the first step, which is imaginative step. Actually, you imagining something is there, a very very small interval, almost of length zero but not zero. And what do you do in the step number two? Step number two is basically just use some sort of approximation. There's nothing serious happen in step number two. You calculate the average rate of change by using the formula which you already have. So because you have already imagined in step number one, there is a imaginative interval exist, and on that imaginative interval, you calculate the average rate of change. And now we come down to the step number three. This is the main step of this basically whole big idea. So as in step number one, we have imagined there is a second point, and the distance from the first point is non-zero. In the last step, you assume opposite to that. Now you assume that distance which was a non-zero, it is actually going to zero. This was the big idea. It does look like at first they are trying to make some sort of fool of us. They are imagining there was a point, the distance was non-zero. In this step number three, we sort of again imagining something is not non-zero distance, or it's a zero distance. But if you look at first, this look like a illogical idea. But when you use this idea into a practical application, you will see the power of this idea. So now I'm going to show you one practical application of this idea. To show you the application, I'm going to take two variables. One I'm going to take y, and then another one is x. Because as I said in the beginning, when change happen, they are always happen in comparison to one another. So we need two variable. One is, let's suppose y is me. If I am changing, I'm always changing in comparison to something else, which is x. And when you have a two variable, there must be also some sort of a relation between them. So we establish a relation how these change are happening, and let's assume that relationship is f of x is equal to x square. So as basically they said in the first step, we will assume there is another point which is x plus h, which is so close to the first point x, but it is also away from it, so that the distance between these 2 points is non-zero. So h is not zero. So now we have imagined this interval. So this is in our imagination. So we will compute the average rate of change. So what is the average rate of change? What is the change at the second point minus the change in the first point, that is the total change. And what is the change in the x is x plus h minus x. This is your average rate of change. So if I call this as a delta y, sometimes they call it delta y over delta x. And now I can use the functional relation and simplify my this step. So if I plug that into the function, it's gonna get x plus h, the square of this, and this is a minus x. And the whole thing is a divide by, so this x cancel out, then you have just h. Now next I'm going to do is I'm going to FOIL the top. So if you FOIL the top, you get x square plus 2xh plus h square, and then you have minus x. And then whole thing is divided by h, as you see that we have h. And now you see, so sorry, this was x square. So now you see this x square will cancel out, and you can also pull out h. So h 2x plus h, whole thing is divided by h. So h is a non-zero. This is why we can do these things. So now you get 2x plus h. So this is after using the Call algebra or doing some simplification. Now in step number 3, what the again the imagination is going to happen, but this time is going to happen in the reverse direction. So h is going to 0 this time. H is not anymore 0. So if h goes to 0, we call this dy by dx, because this is approximation now. And we give the name to our imagination. We say our imagination is become limit. So this limit, the concept of limit is also came out, but it's really came out from our imagination, And this is the limit of this average rate of change, divided by h. And if I take that limit to, because this is equal to this, so if I take that limit, I will get 2x. And that 2x is the instantaneously rate of change at the position x. So what is the speed, or what is the instantaneously rate of change at x? It is 2x, which we got by using this three-step idea, which was proposed by our forefather Newton, Leibniz, and many others. So that is the big idea about the concept of calculus. As long as you believe in it and you follow these three step, or I would call three rule, you will be able to get the instantaneously rate of change or instantaneously speed if you are using your relation as a speed. So what I want you to take away from this whole presentation is this big idea, these three step, or mainly in step number 3, that sort of magic idea which we learned, that if we use that big idea, that is the whole idea is behind the concept of derivative, or the concept of actually this whole calculus. And that is the big things which you can take away from this presentation. So now you may be wondering why I'm showing you this picture. The person in this picture is Professor Gilbert Strand. He is one of my favorite professor. And I'm gonna leave you with the thought what he said about calculus. I watch a lot of YouTube video, and I like his teaching style, the way he teach. So let's see what he has to say about calculus. So he said calculus is not about a variable, it is an idea what is the calculus is about. So my goal was to show you that idea, at least give you the flavor of that idea. What is the main idea or essence of calculus or essence of derivative, which is behind this whole concept. And then the other mathematicians came, and basically what you read in calculus or what you study in the calculus, whole calculus has been invented, but it was based on that the idea which I was trying to show you. So this little idea, the story of this little idea does not stop here, it continues. So it doesn't end here. And what is next in this story? So the next in the story is the life of Epsilon. So this little idea is going to grow, you know, and it's gonna become a very big idea which is gonna invent so many things in mathematics. So there is going to happen the birth of this epsilon, and this epsilon is going to basically change the whole whole history of mathematics. And who gave the birth to this epsilon, and who basically nurture this epsilons, and I'm gonna show you the few mathematicians or the few basically our forefather or our hero, which basically contribute to this the life of this epsilon. So they are the Bolzano, Weierstrass, Cauchy, Riemann. So they are the few names. There are many more names, but what I want you to leave with that, or what I want you to motivate is to take, if you take the real analysis class, you will see the life of epsilon, and you will see how the idea which I show you today, it going to become more logical and more rigorous. It will become more rigorous. It's not just like you might say that it was they're trying to make fool of us. This time it's gonna become more rigorous. It's gonna become more logical, and it's gonna become more beautiful. So this is all I have to say today, and I thank you very much for your time.